Okay, hello everybody. What is a linear map? What is a linear map? So maybe we'll say it first in pictures, or we'll draw it first in pictures. So let's say L for linear is a map sending the line into the plane. So maybe here's the line, and L is going to send it now to the output space, which is two-dimensional. And for linear maps, the only thing that L can do is send a line to some other line. And so that's what it looks like in pictures. So sort of like it can't send it to some curve because linear maps, the image is always flat. Okay. Let's see. Let's try. How about if L? What if L was a map from the plane to space? Okay, well, what would that look like? So we have the plane, the input space is the plane, and then L maps it over somehow to an output space, which is three-dimensional. And what does it look like? Well, if L is linear, then it takes the whole plane and sends it to some plane inside of three-dimensional space. Okay, so like this whole two-dimensional plane goes to some two-dimensional plane. Okay, and so that's what a linear map's like. Linear maps look like this. This is what they look like. Okay, and let's see now, what is a linear map in formulas? Okay, so in formulas, we write down, well, later our linear maps will be the derivative of f at a point x, and it'll send some Rn input space to an output space Rm, maybe a different dimension. And this will be the name of our linear map. But for now, let's just call it L for linear. And so what does it do? Well, it sends, it has a property. So L, this map L, is linear if L applied to a linear combination of vectors, of input vectors, is equal to, and now what I'm going to do is I'm going to pull this summation out. And this is very special. You can only do this for linear maps. And in fact, I can even pull the scalars, these real numbers, Ci, I can pull them out. And then I just apply the map L to the vectors. Okay, so this, and so maybe I'll make this more concrete. If I had C1 V1 plus C2 V2 plus dot dot dot, then that would be equal to the number C1 times the vector L of V1 plus the number C2 times the vector L of V2 plus dot dot dot. So you see I've pulled out the summation, and really I just apply the linear map to each vector, and then I add up the outputs in a linear combination that is exactly identical to what it did to the inputs. So this is a very special property. And I should say where each of the Ci is a real number and each of the Vi is a vector. Well, a vector where? Well, the Vi, I have to get something here that's an input space, so it has to be Rn, right? That's the only thing it could be. So you'd actually already know, just because I wrote this down, you know that the inputs have to be n-dimensional vectors. So that's why I say that the Vi are each n-dimensional vectors. And so a consequence, and so L of the Vi will be, well, they have to be in the output space, an m-dimensional vector. So each of these is an m-dimensional vector, and we're scaling them by real numbers, and then we're adding them up. Okay. So that's what it is in formulas. So let's be even more concrete. If I had, like, let's say, instead of just random vectors, v1, v2, v3, let's take the basis vectors. So if I had 2e1 minus 3e2 plus pi times e3, let's say my input space was R3. then what is required to be true, if L is linear, then it must be true that this is identical to what we'd get if I first did L applied to E1, and then I added it to minus 3 times L applied to E2, and then I add it to pi times L applied to E3. And so you see that the linear combination of E1, E2, E3 with coefficients 2, minus 3, and pi goes to a linear combination with the same exact coefficients of now these vectors that the map L maps over. So as a consequence of this, if I know how L acts on the little basis vectors, I know it everywhere. I know it everywhere because I can write any vector as a combination of those bases. So in particular, like let's go back to our pictures. In pictures, let's say this is the point x, and then f of x is somewhere. Maybe this is f of x. Oh, okay, I've called it L, so this is L of x. Right, so L has to map x somewhere, so maybe here it is. And then look at E1. E1, well, we're in one-dimensional input space, we just have E1. Where does it go? Well, let's say it goes here. It gets stretched out and it gets pointed in that direction. This is the vector L of E1. Once I know L of E1, I know everything because, like, let's say I'm wondering what the linear map does to this point. Well, it has to go to the same linear combination. In other words, it has to go to this point. Okay? And if I'm wondering what does L do to this vector, well, this vector maybe is minus 2e1, then this property says that it has to go to minus 2 L of e1. And if we know L of e1, here is L of e1, then minus 2 of it is, well, what's minus 1 of it, minus 2 of it. So it has to go here. So this is the vector L of minus 2 e1, because by linearity, this has to be minus 2 times L of e1. Once we know L of e1, we know everything. This is the main thing. Maybe I'll put it in words. Is that, well, first of all, so for linear maps, once we know where they send the basis vectors, EI, we know everything. Okay, so another way to say that is we just need to know the outputs L applied to the EI, and then we know L of literally anything. Because that vector V, that arbitrary vector, is equal to V1 E1 plus V2 E2, and by linearity, since we already know the E1 and E2, where they go, we know everything. We know L of V for all V in the input space. Here's another way to say, so let's look at that in pictures. So let's say I'm at the point, let's say this is my point X, then L of X is somewhere, like maybe L of X is there. Okay, then if I know the vector E1 is sent to this vector, L of E1, and then if I also know that the vector E2 is sent to this vector, then I know everything. I know everything. Because, for example, like let's take this green vector here. That vector is equal to minus E1 plus E2. You agree? This green vector sort of looks like it's minus E1 plus E2. well then I know where it's sent. I already know, even though I just told you the images of those, what I say is that well, it has to go by this linearity property. It has to go to the same linear combination, namely -1 of L of E1 plus 1 of L of E2. So I have to go -1 of L of E1 and then +1 of L of E2. And so I go here. That's where it goes. And so what really happens is, like, if I just look at this little unit square between E1 and E2, that is going to go to some parallelogram between L of E1 and L of E2. Okay? And the same thing, like if I look, so really I just can keep getting, like, where does this go? Well, that has to go to this parallelogram. It's sort of hard to draw, but. And what about this one? This little unit square. So here they're unit squares, perfectly sized unit squares, and then they go to parallelograms. Okay, I'm trying my best to draw them sort of roughly the same. They should all look the same. And so you see that just by knowing the L of E1 and L of E2, L of E1 and L of E2 determine everything. They determine how L, everything about the linear map L. That's why we like linear maps. Because linear maps respect linear combinations. That's sort of a way to say it in words. In formulas, what that means is a linear combination goes to the same linear combination of the output vectors. And so it's especially nice when we, like, I could just take this formula and write it again differently as L of a sum of the VI's EI's, and now here VI was a vector, but now it's going to be a number. So why don't I say CI's EI's is equal to the same linear combination, the same scalar real numbers, but now applied to the L of EI's. And so, L of C1 E1 plus C2 E2, if we're in two-dimensional input space, has to go to C1 L of E1 plus C2 L of E2. This is really great because the consequence of this is that linear maps are flat. They give flat images. And they're really easy because all we need to do is figure out what does the linear map do to the basis vectors. Okay? For linear maps, once we know where they send the EI, we know everything. Okay. In the next video, we'll see that the linear map that we'll be interested in is the derivative of a nonlinear map. Right, so a nonlinear map might take this whole line and send it to some curve. A nonlinear map might take this whole plane and send it to some surface. Right? And so nonlinear maps are sort of crazy. Who knows what they're going to do? But linear maps are nice. And so if we had some nonlinear map from Rn to Rm, it would be nice if we could find some linear map, the derivative of f, that near a certain point will be a linear version. Is the linear version of f near the point x. So that's what we'll do in the next video.